Log on, tune in, find out. Another good idea from Cambridge.
Part of our seminar series, always on Tuesday, which we enjoy very much. The second speaker, we have somebody which is coming a bit closer from Paris, Paris-Dauphine, François Bolley. And he's going to talk about joint work with some very unknown people.
So yeah, they are the two usual suspects. So thanks for the invitation to talk. I hope here the organizer won't mess up with the board if we do it here. No. And so there have been many recent works on stochastic particle system related to swarming models. The idea is to study a large system of n particles in RD. Okay. Which state is given by their position and their velocity. So you have the position xi of t and the velocity vi of t, and I is between 1 and n. Okay? And the particles here, I mean the models people look at in swarming is fish, birds, bees, ants, humans, everything. And so the idea, I mean, I won't look any specific model, just the idea is we want to give a general framework to prove the mean field limit from the particle system to the kinetic PD in the end. Okay. So the effects you want to consider among the particles, they are of different kind, and we'll see them in the equation which terms you want to consider. Okay. So the evolution you have in the particle is, so for the position there is no surprise. And the velocity equation, here you see the effects you want to consider now. So first effect is you want to take into account some attraction repulsion force, which means that for you're going to have some interaction of this form, gradient x of u of xi minus xj, okay? And u can be, okay, I'm going to consider only smooth forces, yeah? If I forget to say it later, there won't be any singular potential. And so you want some short range attraction and, short range of repulsion and long range attraction. So more or less you want to consider potentials u which have this kind of shape, okay? So you have first repulsion and then attraction. And models like this were considered by Bertozzi, Dorsonia, and co-authors. Okay. So this is the first effect you want to consider. Second effect is that sometimes they want to reach a certain speed. Last week we saw a talk by Vlad Panferov where he assumed that the velocity, the length of the velocity was fixed to be 1. Okay. Here we want to say maybe they want to reach some velocity but not quite, and so they want to reach some given velocity, and it can be achieved by modeling like plus say alpha minus beta vi squared times vi, which means that if the velocity is smaller than the alpha over beta square root, then you speed up, otherwise you slow down, and you want to reach this velocity alpha over beta square root. Okay? So this is not an interaction, just your own velocity. Okay? Third effect is some of these species here, they want to go like in flux, like for birds at this time of period, they want to go to Africa with all the same speed. Okay? And so a term which can model this, it's some was introduced by Cooker, Snail, and Snail. So it has a form like minus 1 over n sum over j of say vi minus vj, which means that you want to have to get the average velocity of everybody. Okay. So here you want to reach average velocity of the whole group, okay, of the particles. And maybe you are more influenced by particles, I mean birds which are close to you than from these which are far. So maybe this you have to change a little bit, and it depends maybe on the average, on the difference of position, maybe on the modulus of the average position, or these things. Okay. In their model, A of x was like 1 over 1 plus x to the beta, which means that if you're far away, then you don't see it. If you're close, you see it more. So this is some third effect. And another effect you want to consider is randomness. Okay, let me put it here. Randomness, so you have a diffusion coefficient, sigma, which can be a constant, can also depend on the where you are, on the people around you, on the velocity, and now time Brownian motion. Okay, we'll model it like this. Okay. So all this 1, 2, 3, 4 effects that we want to put together, and so the general equation we are going to look at. So it's going to be dxi over dt is the velocity, and dbi over dt. So you see that you have exterior forces here. So it's going to be f of xi vi, okay, with a minus. Then you have interaction terms, which are the term 3 and 1 above here. So it's going to be 1 over n sum over j f xi minus xj vi over bj. Okay, it doesn't have to be a convolution like this, because maybe it's not always radially symmetric the way you are influenced by the other. It could be more general than this. And you have so the random term, which is sigma, which can depend on the what, times the Brownian. Okay. So this is in this form we are going to look at, because we won't give any specific feature of each of the models. Okay. So we'll focus on this particle system here. And I is between 1 and n. And we see from this mean field term here how the particle xi vi is influenced by the other ones. Okay. We'll write it also, if you write z to be xv, we'll write it like dzi is minus f of vi minus 1 over n sum of h of vi minus dj plus maybe another viscosity coefficient dbi over dt. Okay. So we write it like this. Okay. So now what's the question? The question is what happens for n going to infinity? What is the limit description of the particle system that you have here? Okay. And of course you don't want to compute the exact position of each of them. What you're interested is in average quantities, statistical quantities, and quantities to be considered is quantities like 1 over n sum of these observables here. These quantities are given by the empirical measure. By the empirical measure. And what the empirical measure is, okay, let me write it this. So it's a measure that gives rise to this term. So it's 1 over n, the average of the Dirac masses at this point. Xi of t vi. And really this is the object because it gives you what the portion of the system in a given set A. Okay? So this is the key object. The other key object is first marginal is the law of any particle. Okay? So in symmetric and random setting, another interesting object is the law of one particle. Okay, I'm going to write it mu t and then put a 1 here. So it means the law of one particle, then we'll see the law of two particles. And in the symmetric case, it's the expectation of the empirical measure. Okay. Yeah. It gives you what the probability of being in a set A if you look at just one particle. So these are the two objects here. And so the question that we want to answer is what happens when n goes to infinity, which means here the question is what's the limit of the empirical measure and of its average, which is the law of one particle, as n goes to infinity. Okay? This is what we want to answer. Maybe I want to make a link with the talk of Vlad Panferov last week. In the deterministic case, which means when sigma equals 0, then the answer, I mean, at least formally for this smooth potential, is that the empirical measure is a weak solution of the Vlasov equation. Okay? The mu t is a weak solution of the Vlasov equation, which is associated to this, which is b mu dt plus v grad x mu, and then you have this term here, which is going to be f plus h convolved with mu t equals to 0. Okay, in R to D. So it's a weak solution of this. Okay. And so if initially mu hat, so if at t equals 0, mu hat, remember this depends on n, is a n particle empirical measure, it's close to a measure mu 0, okay? Then what you expect is that at time t, the empirical measure at time t, so the mu at t, is going to remain close from what? Well, from the solution of the Vlasov equation starting from mu 0, okay? Solution at time t with initial data mu 0. Okay. So this is what you expect, and so it what you have to prove is some stability result for solutions of the Vlasov equation. Okay. Okay. If you have some stability result on the Vlasov equation. Okay. And this was solved in different settings. So solved. So for globally Lifshitz F and H, which is the exterior force in the interaction by Brown and F. In 77, and then there's work by Luboshin. 79. And then it was written by Neunzer by Spohn. And so for which, what he proved that for some distance between solutions, it has to be a weak distance, no? Because you want to apply it to the empirical measure. So you want to be able to compare really weak solutions, okay? And so for a weak distance, you prove that for any two solutions, so let's call it mu t and nu t, is smaller than the initial distance times some factor. I'm writing a L. It depends on the Lipschitz norms of F and H. Okay? And this is really weak distance linked to optimal transport. Okay? Then for so recently my two fellows, no, not fellows, these two guys here with Jesus Rosado. They consider the case where you have only locally Lipschitz forces, okay? So still the smooth forces, no singularity, but at infinity it can get really large, okay? So for locally Lipschitz S and H, they manage to get better, and but the drawback is that you have to consider compactly supported solutions. You start from a compactly supported initial datum, then it's the forces are Lipschitz on the support, and then you have to play between the way the support grows and the Lipschitz norm on the support of the solution. You have to go like this. Okay? And so here, in this case, you get this result, but with LT, this term here, is going to depend on the initial support. Okay? So of course, now the question would be for the Vlasov-Poisson, okay? And for this, you cannot do this. There is still a stability result in the Vlasov-Poisson. for solutions with a bounded density. Okay, if rho of x, which is the space position density, is in L infinity, okay, in Rd, okay, say in R3, okay, then you know that the forces, the gradient U coupled with rho, okay, it's not globally Lipschitz, it's a log Lipschitz, okay, so it's more than x minus y, log of 1 over x minus y, okay, and so in this case, for solutions which have L infinity density, okay, what you had here, if you call d the distance, it's like d prime smaller than ld, okay, the inequality you get, and by the Grunwald inequality you get this. In this case, if you compare two solutions with an L infinity macroscopic density, what you'll get is like in the Udovich method for the Euler, you get d prime smaller than d log 1 over d. Okay. And this gives stability still. Okay. But of course, you cannot use it for our particle problem because you need the L infinity norm on the row. Okay. So it was just a remark. So I think I'm done with this thing on the deterministic case. Was to recall what Vlad Panferov talked about last week. Now it's going to be different because the empirical measure is not going to be a solution of any kinetic PDE interlimit. Okay.
May I ask you a question?
Yeah, sure.
In this last result, you're assuming the rho is also depends on theta.
Yes.
So that it's in an infinity uniform in time.
Maybe it's on 0 capital T, you do the thing. Okay, you fix capital T. And if you have a bound on 0 capital T, what you want is stability, huh? But it's not a long time. Everything blows up in time. Okay, there is no long time stability. It's just for fixed time intervals. Okay, and this is resolved by Grégoire Loeper. It's in 2006. It's a modification of the argument for the Euler 2D. Okay. What do you get this? Okay. I mean, I didn't want to say more on this. And so for Vlasov, but for potential less singular than Poisson, there is a work of Ray and Chapin. For singular potential. In 2006 also, but not as bad as the Poisson case. So, okay, let me go back to our equation, so the stochastic case. So with diffusion, and so we have everything here. So the equation is here. Okay, so we have this exterior force here, the interaction here, where we see that the evolution of xi vi is given by all the other guys, xj, vj, and you have this Brownian motion. Right? So maybe I will take, for the argument, I'm going to take sigma constant, but you can have it depend on the xi, the xj, and everybody. Okay. So here the difference is that the empirical measure, so mu hat, okay, is not going to be a solution of anything. I mean, you can try writing the evolution of this, and if you write it, you do the Ito calculus, you gain the same beginning as you had here. So d mu dt plus v grad x mu minus f plus h convolved with mu. Okay. You get the minus here, minus sigma over 2, in case it's constant. Otherwise, more complicated, Laplacian v of mu in a weak formulation, okay? But here it's not 0, you expect to have 0 here, no? In fact, you don't have 0. If you take the bracket with the test function phi, you get something which is 1 over n, the sum of, I don't know, gradient phi of, should be maybe, no, if it's xi, vi, time, no, sigma dBi over dt. I mean, it's not 0, but in fact it's small, no? It's small for n going to infinity. So you cannot plot an equation on mu. You still have this remainder term, but it's small, and for n going to infinity, it's going to be 0. So you expect is that for n going to infinity, you expect this empirical measure mu t, okay, to be close to a solution of this equation with the 0 on the right hand side, okay, on the equation on equals 0, okay, and this equation is called the Makin-Vlasov equation. Okay. And in fact, this is going to be what we will prove, is that in the limit, the empirical measure gets close to the solution of the Makin-Vlasov equation. I mean, of course, there was no reason for the empirical measure to be a solution of this equal to 0. No? Why? It's because if you solve this equation with 0, you expect solution to be smooth for positive time, no? Even if it's just in V, you expect it's going to be fine, no? And the empirical measure is a singular measure at any time, no? So it cannot be morally solution of this equal to 0. Okay? And second thing is that if initially the particles are deterministic, there is no randomness initially. With the Brownian motion, this is a random object, no, for any t. Okay. Whereas if you solve this equal to 0, starting from deterministic initial datum, it's going to be deterministic. No? So there are two reasons why this empirical measure, it cannot be really a solution for fixed t, fixed n of this. Okay. But it's going to be close to a solution. Now let's look at the second object we had, which was the first marginal, which was the law of one particle, which we wrote mu t1. Okay. And you want to write maybe the evolution of this object. Okay. Now this is a measure on R2D. Okay. And it's a deterministic measure. Okay, it's the distribution of one particle. Okay. So you write the equation like in the BBGKY hierarchy. You write the evolution, you get d mu over dt plus v grad x mu minus divergence of f mu. And then, so this is the exterior forces, then you have the interaction. The interaction is going to be the integral of h of x minus y, v minus w. And here you don't have the law of one particle, but since you are considering the interactions, you have the law of two particles. So it's going to be mu t2 xv yw. Okay. You're integrating among the partners in the direction. Okay. You're integrating over the other c in R2D. And minus, so sigma 2. So again, here it's not close because the evolution of one guy depends on the distribution of the two. So it's not close. Because the law of two particles is not the product of the law of just one. The law of two is not the law of just one. Okay, so you cannot factorize this. since if you take one particle 1 and particle 2, they interact because of the interactions, which is interaction is this, di minus dj, between any two given particles I and j. Okay, you get correlations which are created in time. Okay? But the thing is that this correlation between particle I and j is small. It's like 1 over n. Okay, and so for n large, what you expect is that they are going to be more or less like independent, and the law of couples, this, is going to be close to the product of the law, which means that Z1 and Z2 are going to be almost independent. And now if you manage to prove that they are almost dependent, which means that this guy mu T2 is almost its product here, then you can factorize here, and you get again the Makin-Vladov equation. Okay. Independent and with law, their law is this, but it's going to be close to a solution of the Makin-Vladov equation. Okay. With law mu T, solution of this equation Makin-Vladov. So in the end, what do we want to prove? All these questions. So for n going to infinity, we want to prove that the empirical measure is close to a solution of the PDE. We want to prove that the marginals also are close to a solution of the PDE. This was the expectation of this. Okay. So first thing, second, and third thing is that the particles, they are almost independent. So particles tend to be independent. Yeah. And this is called propagation of chaos. Meaning that if initially they are independent or close to be independent in n, then for later time they remain almost independent. Okay. So those are the three things we want to prove on this equation. And so the argument, which is now classical, is due to Schnittmann, and is to prove all this, just one single result to get these three results, and it's by a coupling argument. Okay. So the argument, and so the method is due to Schnittmann, is by coupling. Okay. So what do we want to prove? We want to prove that the particles tend to be independent, okay, with law mu t. Okay. So do we know any particles, n particles, independent with law mu t? So independent, n independent particles with law mu t. I mean, can we build them? They are artificial processes. No, we want to introduce them for the method. Well, what do they have to satisfy? I'm going to call them x bar and z bar. Okay, t. So we build them for the proofs. Okay. What do they have to solve? They have to solve this. Dt. So for this, so you assume that you know solution mu t. Okay, solution, Makin-Vladov equation. You consider a Brownian motion Bi, so that will be independent. Okay. So it's a way of creating such processes. Okay. And now the idea is to prove that our processes that we had in the beginning, so the xi, vi, they're going to be close to this particle x bar I, v bar I. Okay. Now what we want to prove that xi of t, vi of t, okay, is going to be close to x bar I of t, v bar I of t, okay, for n large. Okay. So for this we force a little bit, and for this we impose that initially they are the same, okay, xi of 0, and the same with the v's. Okay, and you force them to be driven by the same Brownian motion. Bi is bi. Okay, so this is a coupling trick. Is you force them to be driven by the same Brownian. Okay. So in the end, what do we have? If we sum up all this, so the result, so still by Schnittmann, I mean this is the method. So if initially you start from xi0, vi0, independent with the law mu0, okay. If you take independent Brownian motions, okay. And if now f and h are global Lipschitz, okay, then what you get is that the xi vi are really close to the artificial x bar I v bar I, meaning that xi of t minus x bar I of t squared plus the same with the velocity. Okay, in average, is smaller than c of t over it. So this is the result. And on mu zero, you ask for a second moment, finite second moment. Okay. So this is the classical result. Okay. And does it answer all our questions? Yes. So what did we want to prove? We wanted to prove first, maybe the most simple one is this one, that the law of one particle gets close to mu t solution of the kinetic PD. Was it true? Yes, because if you look at the Wasserstein distance, okay, between two measures mu and nu, like the infimum of all coupled, let me write z bar, where z has low mu and z bar as low nu. Okay, you take this Wasserstein distance here. Okay, well here you see that xi vi for fixed I, xi vi has low mu t1, the first marginal. Okay, x bar I v bar I has the low mu t. That's how we built it. Okay, so in the end, the distance between these two measures is smaller than this quantity here because you get one realization. Okay, of this. So this quantity here is smaller than this, so it goes to 0 as n goes to infinity. Okay. So it's the first proof of the whether the law of one particle converges to the solution of the PD. Okay. Now what did we want to prove? We wanted to prove that the particles tend to be independent. Okay. Is it right? Well, we see it from here. Just with one, we see here that xi vi is getting close to x bar I v bar I. Okay. And you can do it with 1, 2, or 3 k particles as far as you don't reach n here. Okay. And third thing, do we have the convergence of the empirical measure toward the solution of the PDE? Yes, because if you take one observable phi, and you want to compare phi mu t, okay. What is this? It's the 1 over n sum of phi of, I'm writing with a z, no? Phi mu t. Okay. You introduce these artificial processes you had there. Okay. Plus and minus. Now take square. Two. Okay, and now take the average. Okay. So here what do you have? Fixed t, t6. Look at the variables phi of z bar I. These are n independent variables, and this quantity here is their expectation. Okay, so by a law of large numbers, all this term is bounded by the variance of phi of z bar 1 over n. So if phi is a Lipschitz or something, it's like 1 over n. Okay. And here, well, all of them, they have all the same log by symmetry, so it's smaller than this term here, provided that phi is a Lipschitz. Okay? Times the expectation is the theorem. So it's smaller than 1 over n. Okay? So it's a way of measuring how the empirical measure converges to the solution of the PDE. Okay? So this works for globally Lipschitz forces. Now what we did with the two Rosset is to get to non-globally Lipschitz forces, because remember, so extension, two Rossets, yeah? So extension is to non-globally Lipschitz forces. Remember that the terms we had, I mean, in the instances we wanted to consider, we had some exterior force, which was f of xv was alpha minus beta v squared v. Okay, so it's not global Lipschitz. And the interaction, h of xv, we had a term which was a of x times v, and a was 1 over 1 plus x to the beta. Okay. So if you look at the derivative in x, okay, it grows like v, it's not bounded. Okay. So for the instances we had, we need to consider forces. They are locally Lipschitz, not a problem of smoothness, a problem of growth at infinity. Okay. So we work on the proof by Schnittmann, and we'll see in the proof what we need to do to be able to consider these forces. And so there will be a trade-off between the non-Lipschitz growth at infinity and the conditions you have to impose on the initial datum will impose moments to kill this growth. Okay. So let's see how in the remaining time, what's the proof of this, and what we have to do to get to non-Lipschitz forces. Okay. So what's the proof? Maybe I put this above. Have the equations. So remember that was the equation on the particle system, and there on top we have the equation of the artificial process. Okay, let me put them side by side. Okay. So we want to compare these guys here, xi vi, with these guys here with the bound. Okay. So you make the difference. Okay. So you have d dt of xi minus x bar I is vi minus v bar I. Okay. Then you have d dt of vi minus v bar I. Okay, so I made it simpler by taking constant diffusion coefficient. Otherwise, you can do the same term as the terms we'll have to consider. So I'm taking sigma to be constant. Okay. So you have 0. Here we see where you use the fact that you have the same Brownian. Okay, this is the coupling thing. Okay. And then you have to compare the exterior forces. Okay. So it's minus f vi minus f of the z bar I. Okay, this is for the exterior term, and you have the interaction term, which is this term here, vi dj, okay, minus what? This term here. So now what you want is not you want the square norm. Okay. So you're going to let alpha of t is the quantity you want to consider. Okay? xi minus x bar I, vi minus v bar. Okay. So you look at alpha prime of t. No? So alpha prime of t. So it's d over dt of the expectation of this. If you take the expectation of this, it gives you so 1/2 v expectation of xi minus x bar I, vi minus v bar I. This is for the derivative of this. This is okay because it's going to be smaller than alpha of t. Yeah? This is no problem. Now the most interesting term is the second one. Okay? Now you have minus expectation of what? F of vi plus f of z bar I. Okay. Vi minus v bar I. Okay. This is the exterior term. Okay. And you have now the interaction here. Okay. So you have 1 over n. Okay, now it's h of vi minus vj minus 1 over n minus h average over mu t v bar I vi. So what do we have? First term is smaller than alpha of t. Okay. Maybe 1/2. Now second term, you see that if f is globally Lipschitz, then this is smaller than vi minus z bar I, and you will get an alpha again. Okay. Plus alpha of t if f is globally Lipschitz. Now, if f is not globally Lipschitz anymore, what do you have? Well, if you, for instance, if you do the Young's inequality, you want to bound f of vi, f of z bar I squared. Okay. If you have it Lipschitz, you bound it by L times the expectation of zi minus z bar I squared. Okay. Otherwise, what you do is you cut and you localize a little bit on whether the points are close or far. Okay. So you say it's more than f of zi minus f of z bar I where they are close. So zi, they are all, two of them smaller than r, okay, plus the same term where they are far. Okay. If they are close on a certain ball, well, you will have some globally Lipschitz bound on the ball. Okay. So first term, b is larger than 1 plus some r to some p. Okay. Expectation of zi minus z bar I. Okay. So the ball is globally Lipschitz, and then outside the ball, well, you can control, like e is minus r, say q. Okay. If you have exponential moment over order q. This is okay if you have moments like e to the epsilon z I q is final. With the bar, it is exactly e epsilon z q d mu t of xv. Okay. And the same with the bars, which means the particle system. Okay. So it means that if you have exponential moments, then you can play a little bit to kill the terms outside the ball, okay, and to finish the thing. So for q equal to p, so if you take the same, for q equal to p, then you do the same job with the h, okay, what you're going to get is alpha prime smaller than 1 plus rp alpha plus e to the minus rp, okay. And this term here is the law of large number argument, and it's smaller than 1 over n. Okay. Then you let this to be small r. Okay. And you optimize in r. and you manage to get that alpha of t is smaller than 1 over n to the something like e to the minus t. Okay, it's not anymore 1 over n like in the global Lipschitz case. You lose the power, which gets worse and worse. Okay. If instead you have larger exponential moments than what you assume on the force field F, okay, then you get, so here you get a better power here, and you can do better. You get alpha of t that for every not epsilon, omega is smaller than c omega over 1 minus omega, which means that you get almost to the rate given by the law of large numbers. Okay, so it's almost optimal. So I didn't try in detail the game between the exponential moments you need to assume and the power that you give on the force, but you can write them. And the idea is that on all the examples, the moments that you need to assume the solution, they are propagated. So if you have them initially, then they keep finite at any time. Okay. So I think that's all I wanted to present. Okay. Thanks.
Thanks very much, François. Are there any questions?
There are people taking notes. To bother them.
What was the exact condition on the behavior at infinity for this Lipschitz constant? I mean,
what we're assuming is
was it sort of linear or how can
no, it can be like it can grow. The thing also I didn't talk too much about is that you have to give different assumptions on x and v. Okay. You want to assume less moments on x that you can on v. Okay. And so for the forces, you have this like maybe f of xv minus f of yw. So it's more than x minus y times 1 plus v plus w, things like this. Okay. So the y dip and plus v minus w times d minus w. Okay. That in x and y is global Lipschitz for given VW. Okay. But in the V dependence, it can grow in V and W. Yes. P, yes. So it's not global Lipschitz, but of course it doesn't grow in the position, it grows in the velocity, okay, the relative velocity. And the same for the interaction. And so if you have a different weight on VW than XY, like here, then in fact what you need to assume is moments like x squared plus e to the epsilon gt. Okay. They don't play the x and v don't play the same role because here you don't have plus xp plus yp. Okay. In x it's bounded at infinity, it's Lipschitz. Just in v that it grows at infinity.
A second question. What you need in your proof is that these exponential moments are transported, so to say.
Yes.
If you have the exponential moment at 0, you will have it at all time. This also seems to be not easy to prove if you don't have global Lipschitz. So
yeah, it's true. No, with this I agree. Is to have propagation, you need some assumptions
you
on.
prove this independently. I mean, this conservation, so to say, of these exponential moments of the solution. Or?
Yeah, yes, but the thing is that for these are the kind of assumptions you need for the mean-field limit, just for this proof. But it's true that for global existence or for propagation of moments, then you need some extra. I mean, if you just assume this, maybe the solution could block, no? That's what you mean, no?
Yeah.
So it's true that for global existence, I mean, we proved it, we gave some conditions, and it has to not to grow too fast at infinity. Still, it can grow a little bit more than linear. I mean, it doesn't have to be global ellipse, but it has not to grow too fast. So there is a play between being not global ellipses, because we wanted to introduce the term there, but also that you have to give conditions to have a global resistance. Yeah, of course, if you take x dot is v and v dot is I don't know what v cube or something, it's going to block everything.